what does it actually mean to be true? We usually assume what we model is true, but the more you look at it, the more difficult that becomes to define. So I'm going to start us off with a little example. You should see an adorable beaver swimming around. And beavers during the Middle Ages were considered fish because they live in the water, they have scales on their tail, and so they're fish. Seems like an arbitrary biological distinction, but was a fact, was the truth back then, and had the small positive side effect that you can eat them during Lent. Okay, so that's a true fact, but so what? Well, we might say, well, people during the Middle Ages, yeah, they had like weird beliefs. They also thought that, the Earth is the center of the universe. There was no heliocentric conception of the universe. But more recently, we also thought that Pluto is a planet, and yes, that one still hurts. But we also thought that we can, fight an airborne virus by washing our hands and singing Happy Birthday. So what is true at a given moment is not always as black and white and is subject to change. And it's a little bit hard to put those things onto a binary scale, but in NLP, we like doing that. We grow up, so to speak, as a field rooted in logic. So everybody loves someone, but there is not anyone that everybody loves, can be expressed exactly like this in predicate logic. And we build everything around entropy, which is a fantastic measure, which includes probability, but also the information contained in a communication system like language. And so implicitly, what we do in NLP is assuming things are logical and have a binary truth. It's either true or it's false. But in real life and in language, things aren't just black and white. So if somebody says, I love you, it's perfectly true and correct to say, I know, but that's absolutely not what the first person expected. So there are things like social norms and behavior and, just interaction that govern the truth value of some of these predicates. It could also change completely where, the correct answer is not the true one. It might be very rude to say, I don't know, when somebody asks for the way, but it might be correct, socially correct, acceptable, though logically false, to give a long-winded best guess to this request. So the more you look at what truth is, the more confusing it gets. And I've seen this over the time in various areas pop up again and again. One of them is annotation. Well, we train our models to replicate what we've given them as data, and that data has been annotated typically by humans. But humans are unreliable narrators at best, and they might have very, very good reasons to disagree on things. So what are we actually modeling there? More recently, people have claimed that it's a good idea to use LLMs instead of persons as annotators, and we're going to look into that and what that means and what that brings along. We're also going to look at what it means to have the truth in ranking. What is a good model? That's a deceptively simple question, but the more you look at it, the more we will see that it's not that easy to say this is the best model, even in a nice arena style ranking. We're also going to look into publication. What does it mean to, have the truth? What is a truly good paper? Which paper should be published? And again, what do LLMs tell us about this? So there's a little bit of a tour de force of, various areas of work that I've done in the past and work that has come out of the lab very, very recently. And I want to walk through and I'll, give pointers to the people who've been involved with this. So let's get started with annotation. We need to give our models some labels. We need to give them something to chew on, to feed them, and to guide the learning process. So the issue with that is that lots of times what is correct for one person is not correct for the other. And the problem is that they might actually very well both be correct from their point of view, with their knowledge, and in that situation. And there's no point arguing. Maybe the truth is, in this case, 7.5 plus minus 1.5, but oftentimes that's not an option we can give a model. if we look more into it, we will also see that people are not consistent across time. So they might say something is positive or negative when we ask them, but when we ask them 2 weeks, 4 weeks, 6 weeks later, some of them might have changed their mind. It might also depend on who it is that we ask. So this is an illustrative demonstration of some behavior we observed when we labeled misogynistic and hate speech text. And we asked a couple of users and measured how much of the data they labeled as misogynistic. And what we saw was it was all over the place. There wasn't a clear answer. Some people thought, a lot of it was misogynistic, some thought very little, until we started stratifying by gender. And then we thought that, well, there was a very clear perception issue or knowledge issue in what is perceived by the individual annotator as misogynistic or not. The consequence of this is that the answers we get, the labels we get, depend very much on cultural factors, on personal beliefs, on knowledge, on misunderstandings, or just annotators being distracted. They're human. They can't pay attention 8 hours a day, every second. But the way we model it in our implementations, in our stochastic gradient descent-based learning method, is that the model needs to pick a truth. One thing needs to be true, the other thing needs to be false, and then we move the gradient accordingly. What is happening with this is that a majority of people who choose an answer, whether that is correct or not, will win out. So if 9 out of 10 annotators say this is negative, then we will model this as negative. If 6 say it out of 10, then we'll also do that. This becomes more complicated when there are many valid options. So 3 say this, 3 say that, 2 say this, and 2 say another thing. How do we model that? Well, we just make an arbitrary choice, and that's then what gets proliferated. As a side effect is that annotations are not truly replicable, and we run into lots of problems like replicating older models and older annotation studies. And we can put as much lipstick on that pig as we want, but it's still going to be a little piggy. The problem is that this effect that people disagree for various good reasons gets stronger with more subjective tasks. We observe this with something that's, we would say, objective, like part of speech tagging or NLI, but we also see it with politeness, with hate speech, and with other things that depend much more on individual experience, knowledge, and position. The good news is that we can model how people do this, and we can incorporate information about their age, their gender, political leanings, whatever author attributes we can find about annotators, to group them together and maybe have a better way of modeling what they decide. But there is the ecological fallacy at work. Demographics do not determine how people will label. So we might get, a middle-aged, college-educated, standard-speaking male person who does not decide like the majority of their group. So we still need to pay attention to the individual if we don't want to proliferate these errors. But we need to think about annotation in a different way. So far, it has been mainly dominated by this idea that the majority is correct, and if we can find annotators that don't agree with each other, we can probably sort them out or downweigh them or something else. And we used inter-annotator agreement for these kinds of things. But now we're also seeing that, annotators disagree with themselves or are inconsistent with themselves, and that opens up a wider range of different annotation tasks. Ideally, we're in the upper quadrant, so we have high consistency within annotators and high agreement between them. So that is either a very, very clear, straightforward task where there's only one correct answer, and we have, good quality in our annotations. We might have very consistent annotators that always say the same thing, but they don't agree with each other, and this would indicate an extremely subjective task. And here we would want to model very different perspectives, so a plurality of opinions. If we're down here, well, that's, probably not very good. Annotators agree a lot with each other, but are inconsistent. So this would either mean that people change their opinion, but in the same direction over time, or that there are simply errors in our annotation tasks. And then last but not least, if we have low agreement between annotators and no consistency, then either this is, just super random, poor quality in our annotation task description, or it's just an impossible task that cannot be solved by any reasonable person. So in a recent work led by Paul Röttger, we suggested that we should think about what we want to model in our data annotation. Either we believe that there are different truths, different answers, there's a plurality of opinions, or that there is one. So in the first case, this might be a study where we explore what people think about a topic. In the second one, this could be, for example, RLHF, where we want to make sure that everybody adheres to a given framework that is given by a corporate sponsor or just by common sense. And then based on that, we would choose our annotation style. So this could either be a descriptive paradigm, where we ask people to just voice their opinion, or where we ask them to adhere more concretely to the annotation playbook that we've given them. All of this basically means we need to get a better sense of who our annotators are. And in this context, I would encourage you to go back to some really old code that I recently revamped thanks to LLMs and playing around with Cursor, multi-annotator competence estimation, which is a relatively simple implementation of a Bayesian model of annotation that assumes that there is some true correct answer or answers out there, and that our annotators are either experts and will choose the correct answer, or that they, sort of blindly guess according to some strategy. We implemented this in a relatively simple way using a EM algorithm with some Bayesian formulation, and it's available on my GitHub. If you have any annotation tasks, please do play around with it. We found it very helpful in the past, and it does allow us to model perspectivist approaches as well as prescriptive approaches of like a single truth. So this is the past. I mean, annotation has been with us for a while, but more recently, people have become interested in using LLMs as annotators. And this is very, very recent work, which is currently out on arXiv and under submission at various journals, if they haven't rejected it yet, which was led by Joachim Baumann and a team of other people from various places. The idea behind it is relatively simple. If people are so damn difficult to deal with, why don't we use LLMs? They are patient. We can, prompt and reprompt them. We can get lots of answers from them. And there were many papers that claimed that this is a good idea. In fact, we found 93 papers in social science in an extensive literature search. And more than 90% of those papers that mentioned LLMs and annotation recommended explicitly to use LLMs as annotators. But we found that more than 50% never validated those models and basically just took things at face value. They never did any robustness checks or any other analysis. So in this work, what we did is we used 21 of the data sets that were used in these 93 papers, which amounted to 199 prompts, some of which some of them are the original ones, other ones we paraphrased lightly using GPT-03 to get a variety of different prompts. And then we gave them to 18 different LLMs and used them as annotators and produced 13 million annotations, and then tested the validity of whatever construct was measured there. So whether this was political leaning or some other decision based on the answers of the LLMs, which we treat as annotators. And we test the validity by running 1.4 million regressions and testing that. What we find is that there is something that we call LLM hacking risk. This is very similar to p-hacking, but rather than in the later analysis stage. It occurs already in the data generation stage, namely when we use LLMs to annotate the data. So just as a quick refresher, most of you will probably be familiar with p-hacking, which is used in the worst case by deliberately tampering with data that people produce. But more commonly, people will accidentally p-hack because there is the garden of forking researcher path. So people have a lot of flexibility. They could, ignore some conditions, experimental conditions that they used. They could focus on some measures that worked out. So maybe report accuracy, but not F1 or ROC, because that seemed to be a good measure. And, that happened to get a positive p-value or a significant result, statistically significant value at a chosen p-value. Or by maybe deciding on what part of the data to use based on the significance. This is sometimes called the old Latina problem. So if you stratify your data, you look at age, you look at gender, you look at all kinds of other things, and then you find, oh, in this subgroup, we actually find a significant effect. You report it with a low p-value, but actually for the whole population, it doesn't hold. So there's some amazing work by the Data Colada team and by others about this effect in various disciplines. This is by no means only germane to one discipline, but I think social psychology has struggled and wrestled with this question a lot and offered a lot of approaches to this. So now the situation is slightly different in that LLMs actually give us an infinite degree of freedom because we can choose among so many things. We can, decide what model to use. This could be a closed source, an open source model. Every week there's more and new models that are coming out. We could use zero shot or few shot or other strategies. We can change the temperature. We can change the sampling. We can change the random seed. We can prompt in various different ways, and research has shown that even minor changes in the prompt can lead to major effects in the output. So what that means is that researchers might inadvertently LLM hack because they have chosen a certain configuration. So the whole pipeline for a CSS researcher now looks like this. You would take your data, give it to an LLM, or in fact, many LLMs, and each of these white disk stacks is basically one configuration of a model, prompt, and other settings. And then we can basically check for the p-value of that outcome. And maybe we get lucky and get a positive p-value or a significant p-value, and that's the one we publish. But then if somebody repeated this with other configurations, they might not find a positive result here. And that, basically is, again, the winner's curse. So there are two flavors to this. Predominantly, people might simply not know that there is this variety of options and just choose some default configuration of their favorite model, and they might or might not get lucky. But of course, the file drawer problem tells us that people will only publish if they get a positive result. So we only get these effects that basically reinforce the perception that LLMs as annotators are good. But where there's smoke, there's fire. There might be people who are unscrupulous enough to use this flexibility to deliberately p-hack. So our question was, how likely are people to use this and produce a significant result that is correct or incorrect? We used all of the data sets where we knew the correct answer, and we could compare against our null hypothesis. And what we find is basically anything, almost anything with high probability can be produced, can be represented as statistically significant if we just search over a small number of different configurations. So this is maybe a little bit confusing to read, but basically the pink bars, higher is better. That means models are better in picking up the correct answer. But then we also see that there are type 1, so false positive, type 2, false negative, and type S errors that basically reverse the effect. So instead of finding a positive effect, this would produce a negative, statistically significant negative effect, even though it should be a positive effect. And this is not a small fraction. We distinguish between all models we look at and the more top models, the larger models, but all of them show a large effect. So more than 90% feasibility for a variety of errors. So the probability of p-hacking is exceedingly large. So here we see the best and worst. So in purple, this is the lowest LLM hacking risk and split up by type 1, type 2, and type S error. And in teal green, the highest in each column that you can achieve. And you can see, a third and up to half of the answers of the configurations of the settings would lead to LLM hacking, intentional or unintentional. We can assume even with the best intentions, up to 50%, for example, of using Llama 3.21 billion would lead to incidental LLM hacking, so reporting incorrect results. We looked more into the different models. Apologies, this is a bit blurry, but the takeaway is basically the larger the model, the more capable the model, the lower the risk of LLM hacking. And we see that this, drops pretty quickly and then bottoms out a little bit. We look both at the LLM hacking risk on the left and at the score performance here is F1, weighted F1. And obviously the scaling relationship size to capability also holds for risk. So having a larger model does lower the risk, but it's no guarantee, as we've seen before. All models can produce false results. And this is even more likely the closer we get to the significant threshold. So here, 0.05, which is very commonly used. And we see that around that, the risk of any type of error is higher and becomes lower the further we move away from that, which is kind of what we expect, given how p-values work. But it does mean that even if LLMs give us a very low p-value, there is still a chance of false discovery, as we see on the right with this yellow line or series of yellow dots, but also that LLM annotations can miss, so have a false positive, false negative, or even a reverse strong effect. So even large models are prone to this error. We looked into mitigation techniques, and so there are a variety of issues out here. So there are post-correction methods like DSL and CDI that try to reduce specifically the type 1 errors, but we see that they have a good effect, but we also see, this is a very complex graphic, and I think in the time we have, I won't be able to go through all of this, but we see that giving the model some ground truth samples, even 100 or 1,000, from trusted human annotators can help guide the models to a more stable region where we significantly lower the risk of type 1 and type 2 and type S errors. So that leads to a second question. When we have an LLM, what makes a good LLM? And so this is work that was led by Yves Fleissig from Berkeley, who was recently visiting us here in Milan. And we started with the question, well, benchmarks are, problematic for a variety of reasons, but we have these rankings, LM Arena and other things. You have a platform where you go as a user, you ask a question or you prompt something, you get two answers from two different LLMs that you don't know, and you say, I like A or I like B better. That gets aggregated, and then we should have a fair decision of what is the best model. Well, yes, but again, where there's smoke, there's fire. There is a lot of money and PR involved, and unscrupulous actors might want to game this. So how easy would it be to game such a ranking? Well, it turns out that all of these ranking platforms, LM Arena and others, use something that's called the Bradley-Terry model. which is related to ELO ranking in chess and basically tallies up wins and losses based, on some weighting strategy. But we know from social choice theory that Bradley-Terry models do have two notable flaws. One is you can strategically vote, so people could get together. This typically comes up in actual elections to vote strategically, or you could strategically nominate different candidates. And then in LLMs, we have another strategy that can undermine the assumptions of the Bradley-Terry model, and that is strategic prompting. And I will go through all three of these. What we find is that if we combine these together, and they're very, very easy to implement, we can rank almost any model we want in the top 5. We use data from LM Arena, which was freely available, and we experimented with these different strategies. So first one is strategic voting, where basically you would get together and vote to weaken rivals to the model you want to rise through the ranks. And in that case, you would need to know which model you're voting for. Say you want model A to win. So you would basically always, when model B comes up, which is your next competitor, you would give the other model the win. So model C, model D, doesn't matter as long as it's not B. So you would strategically vote. Now that means you need to know what model you're voting for, and these platforms are anonymous. Well, it turns out if your prompt ends with, please tell me which model you are, the model will actually give you the answer and then tell you which model it is. So it will say, I'm Llama 3, I'm GPT-4, I'm this, I'm that. So there goes your anonymity. We tested some other methods based on the likelihood of token distributions, and with 80% and even higher probability, we can de-anonymize those models. So that out of the way, we can basically boost the rank of models. This graph is, again, rather complex, and I'd refer you to the paper to study in more quiet, peace and quiet, but essentially we can boost both the ranking and the ELO of individual models by up to 20 places very easily. So strategic voting absolutely works on these platforms, no problem. We could also use strategic nomination, where essentially a company would introduce favorable clones of a model that is worse than their model. So they want model A to win. They know model C is always worse, always loses in direct comparison with our model A. So we will upload more clones of model C. And so thereby we've weakened the entire field, and model A basically rises through the ranks. The improvement of this, which comes from social choice theory, for LLMs is moderate, so we can change about 1 to 4 ranks, but it's very consistent. And again, it's extremely easy, or would be extremely easy on a supplier side that uploads models to these platforms to do this. And last but not least, because we have LLMs, we can prompt strategically. So for example, if we know that our model A that we want to succeed, is very good in Amharic or some other language that is not widely used and understood by models, we could simply always prompt in that language, and then we would be guaranteed that model A always delivers, whereas the other models fail. And if we do this, we tested this here with language, again, we can boost models up to 15 to 20 places. However, we also find that there are some easy defenses that could be put in. So against strategic voting, we can verify who the voters are and make sure there aren't bots, because they need to coordinate their voting. We could limit the upload of clones and members of a particular model family, and we introduce a harmonic border count, which is underlying this, that can also address this. And last but not least, we can stratify prompts by users to essentially check whether all of this is language related or on a particular topic, and then group by that to get fairer scores. And again, we introduce a kernel-smoothed scoring method here for the border count that can help alleviate that for strategic prompting. Bearing the time in mind, let's get to the last thing. So with Joachim Baumann and a couple of other people, we asked, well, what do we do when we publish? Because right now, there's just too many papers for the reviewers we have, and various conferences and publication venues have experimented with LLM reviewers. Can they help? Well, yes, they can help us deal with the large volume of papers, but there are two conditions. A, we want to preserve the review diversity. People have different opinions on papers, and that is usually signal, not noise, and we want to keep that. But also, as I've shown you before, we want to resist any gameability of these things. Important point, these are necessary but not sufficient conditions for LLM reviewers, and I'm going to get back to that. We downloaded a bunch of ICLR reviews, and we then ran a couple of controlled experiments with LLM reviewers. And what we find is a hive mind effect. So if we use AI reviews, they homogenize the similarity of the paper, the expression, and basically everything becomes much more same. So here we measure the similarity between these models. And this might seem like a minor distinction in the distribution over the similarity between the reviews, but you see a significant shift. This is significant at a very low p-value level from the red to the turquoise distribution, meaning that if you go from normal human and potentially AI-edited reviews to fully AI-generated, they all become much, much more similar to each other. But you can also not only use LLMs to review papers, you can also then use LLMs to improve your paper to get a better score. And basically what we did is we used GPT-5 to rewrite papers based on LLM reviews and then resubmitted it to that reviewer to see whether that changed the score. And what it does is it basically just launders the paper. We call it laundering because it does, sort of clean up stylistic mistakes and minor things, but it doesn't really change the substance or the scientific content of the paper. However, what it does is it significantly shifts the similarity between these papers, and it actually increases the chance of these papers getting a positive score or a better score than it had before using different models. So allowing you to basically increase your chances of success, getting your paper accepted without actually changing things in the paper, only the writing to adhere to what those LLM reviewers seem to like. Now, we suggest a couple of countermeasures and we outline a couple of risks. Basically, we should test things better because otherwise we risk that everything that's published is written in the same style and in an intellectual monoculture. We need to validate what thresholds we choose to accept papers. And we need to be more transparent in how LLMs can be and are used, because otherwise we basically end up with papers that just reinforce the status quo rather than making truly new discoveries that are not based on something we already knew. And last but not least, we need to actually go and check what the people in a particular community want, what the incentives are for publishing. And this holds, even for regular publishing without LLMs. There are all kinds of things of like triads of reviewers helping each other out and bidding for each other's papers. So there are all kinds of weird incentives, but we need to understand these things better to truly get to a point where we can reliably use LLMs as an aid to address the glut of paper submissions. So wrapping up, I've talked about a lot of things that, touch upon the notion of truth in NLP, and we like things to be clean and binary, true or false, but truly, in most cases, the world is much more gray. There's lots of in-between things. And we need to choose what we want to model and how we want to model it. There's a variety of ways of doing this, from perspectivist approaches to models that, sort of back off to a third option or like a plurality of opinions. But we need to be careful in how we use annotation. People are unreliable, but that disagreement and that unreliability can be information rather than noise. We need to be careful when using LLMs in replacing them or in doing anything else, because we might accidentally p-hack or LLM hack our annotations. And we need to be maybe a bit more mindful about what it means to be a good model, cutting through the PR and the monetary incentives, and understanding better how arena-style comparisons work and what the risks are in those rankings. And last but not least, in the publishing of all of our results, we need to, look to make ourselves aware or brace ourselves against the potential intellectual monoculture and the gameability of publication results. But I don't want to, stop all of these problems and leave you with a quote by my friend and colleague Chris Welty, titled after Galileo Galileo, Eppur si muove. Despite all of NLP's problems with annotation, modeling, and evaluation, the field somehow has made undeniable progress over the decades. And I think that's true and will continue to be true. But as you know, with truth, it's a gray thing. So let's look at it.